Okay, so रिकॉर्ड ये हो रहा है, yes. So we have
सर
learned a little bit about.
जो है वो कौन सा कोर्स कर रहे हैं ऑफर?
हाँ?
आप नेक्स्ट सेमेस्टर कौन सा कोर्स ऑफर कर रहे हैं?
Next semester यही GR2.
सर आप क्वांटम का कह रहे थे?
Yeah, I'll do quantum aspects in GR.
अच्छा ओके सर, क्योंकि कुछ बच्चों का ना वो
So all of the effects of gravity arise from the fact that the inertial frames are not extendable. To neighboring regions. And this very fact that they are not extendable to neighboring regions, this means that there is curvature. So what we have seen is we did this theorem that in any manifold at a point you can go to coordinates or coordinates exist. Coordinates exist in which at a point the metric takes the flat form. So that's what you assume. No, not assume, this is just a fact. So what you say is that there will be some special coordinates, and in physics these coordinates we are calling them frames of reference. So you can choose a frame of reference in which the metric takes the flat form. So it's just the Minkowski metric. And then you say that in this coordinates, the physics is just the usual physics of special relativity. And hence, the physics is just the usual physics of special relativity. Of Newton, but not just Newton. Newton modified according to the principles of relativity. Minus the gravity, there's no gravity. You do not minus gravity. Gravity just does not exist. So you go to, so this is the prescription. Go to locally. By locally you mean at a point. Initial frame. This means go to a frame, go to those coordinates in which the metric takes this form, and you are guaranteed that these coordinates will exist at any given point. So go to this and then use physics laws as if nothing has changed from special relativity. But then once you have written this law, write this law, write the laws in tensor form. What does that mean? Put them in coordinate independent forms. What does that mean? That means they exist so that they hold in every coordinate. That's what a tensor is. The tensor law, it holds the form of the equations is same in all coordinates. Equation is same in all coordinates. So once you have done it, written them in this form, then just elevate them, then just declare that this law holds in all coordinates. So this becomes a geometric law. So the way you derive it, because you have this machinery available that you can go to initial coordinates where things are just as if you have special relativity. You write the law there, and then you give it the form of a tensor law so that it holds in all coordinates. But we know that this would be true even if there's no gravity. But now what we are saying is that once we give it this form, then if at other places, I derived it over here, putting metric equal to eta, at other places, the metric may not take this form. It would be some other g, but the law would still hold. So what's happening is you have the usual laws. It's just that the manifold at other places is curved relative to this, and the law gets modified according to that curvature. So what would be the example? So first is law of motion. So the law of motion was just the Newton's law. So it was same in special relativity, that things move at constant speed, or material particles, they move along. Material particles or particles world lines are straight lines. So that would mean I go to a frame where the metric components are -1, 1, 1, 1. Then I write the special relativity law, which is this. That's the equation of the straight line. I can write it in this form. But over here, this is not a tensorial law. It doesn't hold in all coordinate systems. Even if there were no curvature, if I go to a general coordinate system, this form of equation does not hold. So I try to give it a form which is a tensor law so that it holds in all coordinate system. So that I can do is by doing this, just introduce the chain rule. Even now, this is not all components over here are tensorial. This is the tangent vector, which I know is a tensor because it's a vector, it's a proper vector. I should probably make it new. Too many news. So this is a vector. The thing which is not a tensorial object is this, because I know that this does not transform as a tensor. This is appearing here. I know this is appearing here because I am in inertial coordinates. At this point. So at this point, this is, so to speak, has proper form because in inertial coordinates, this is a tensorial object. But if I want to make it a tensorial object in any general coordinates, replace it. It's not really replacing. It's just writing it like this. Because in this particular coordinates, these two things are same. But once I have given this form, this is true, can work, I should say can work. In all coordinates. So I elevate the law to this law. That's the law of motion. Now, if there is curvature in the space-time, that would be captured. Curvature would be captured in this equation through the metric and connection. We know that connection is derived from metric, through the metric, or connection is the one and the same thing. And this is just the geodesic equation. So what you have said that particles still move on straight lines, but these straight lines are curved because the underlying manifold is curved. In other words, these straight lines may not have the same behavior which we are used to. They're just the straight lines of the curved manifold. And there's no gravity. Gravity never appears as force. You just have the straight lines in your curved geometry. And this curved geometry appears because of gravity. Now, so this becomes your law that particles follow geodesics. Suppose you want to do electrodynamics. You have charged particles, charged fields, light, whatever, near some gravitational field. And you want to know what would be the law. You neglect gravity. You go to a local coordinate system where your metric is, again, eta. And you just write the law of whatever the law of electrodynamics was in special relativity, in the absence of gravity, which was the Maxwell's theory, Maxwell's equations. This was in one of your homeworks. F beta gamma plus totally anti-symmetric, totally anti-symmetrized. I could have probably just written it out. Is 0. So these two equations are the Maxwell's equations. And this guy is a tensor. This guy is a vector. This guy is not a tensor. So you replace it by covariant derivative. This then becomes your Maxwell's equations in the presence of gravity. And there's no mention of gravity here because all the effects of gravity are contained in how this covariant derivative acts, how it is built. It is defining for you the connection, and that connection is coming from the metric, which is now a curved metric, a metric of on a curved manifold. Now let's see some of this in action. So consider a space-time given by a metric So it's a four-dimensional space-time. And what are these coordinates? We don't know. It's just these are just some coordinates. In this particular coordinate system, you are given some coordinates t, x, y, z. And in this coordinate system, the metric on this manifold looks like this. That's a general problem in general relativity. The coordinates are very general, so once you look at the metric, you can't tell what this metric is telling you unless you explore some physics, because we know that even a normal kind of metric can take very weird forms if we change coordinates. In any case, whatever this thing is, whatever these coordinates are, you are given that this is the metric. This is your initial thing. And this a of t, this is a function of time, function of this one of this coordinate, function of t only, not of x, y, or z. And suppose it has some functional dependence which are given to you. Maybe it's increasing like that, or whatever. T, a of t. So this is all given, and you want to explore its physics. So first of all, the metric, I can write it like this. It's a diagonal metric. G inverse is just this thing. And the first question we want to answer is, what paths do the particles follow in this spacetime? So first of all, we don't know even that if it's a non-curved Minkowski spacetime or not, because even Minkowski spacetime, you did it one homework where you change the coordinates to rotating coordinates. So the metric can develop time-dependent factors even in Minkowski space. So we don't know if it's Minkowski or not. And if it's not Minkowski, it's probably being generated, being curved. If it's a curved, truly a curved manifold, then it's being curved because of some kind of gravity. What will cause it? How will you get it? That we haven't solved. It's just that if you are given the metric, how to extract physics. There's one way to find out if it's a Minkowski spacetime or not, which is that you compute the Riemann tensor of this guy, and then, for example, compute the Ricci scalar. Ricci scalar does not depend on coordinates, so it doesn't matter which coordinate system you compute it in, it will tell you if it's non-zero, it's telling you that you have some curvature over there. So it cannot be Minkowski. In any case, I'm not doing that. I'm just exploring what paths do the particles follow in this space-time. So to do that, the particles just follow this geodesic equation. And to write this, I need the Christoffels. And if I compute the Christoffels, I have half GTT, GT, GTT. You will all have these kind of things. But the GTT component is a constant. So this is 0. Similarly, if I look at this guy, I will have GT x plus dx gtt minus dt gtx. Again, I don't have off-diagonal terms, so these are 0, and gtt is constant, so this is also 0. But this guy, dx gtx plus dx gxt minus dt gxx, these off diagonals are not there. You have a half. GTT in the inverse metric is just -1. There's a -1 coming from here. And then you have d by dt of gxx, which is a square of t. So this gives you 2 over 2 a dot a dot, where a dot is the time derivative of a. Now, similarly, I can find, well, first of all, I can write these other ones. There's actually a spherical symmetry over here. I could convert the coordinates and put it in spherically symmetric form, but this is also fine. I just know that x and y and z, all these directions act exactly same because they appear in the same way in the metric. So this will also be same. A dot a. I also need these guys. These are again 0. This is 0 because GTT, they're all 0. dx xx, it will have all x derivatives, but none of the components depends on spatial. So this is 0. And then I have this guy dt gxx, and then I'll have plus dx gtx plus minus dx gtx. So these are 0, but this is not. This is, well, gxx is not 1 actually. It's the inverse metric, so it had a 1 over a square, and this is a square. So 2 over 2 a dot, so it's a dot over a. So these are the Christoffels. That means the geodesics are d2t d tau square xx dx over d tau dx over d tau plus the y ones this is 0. So this I can write. When I write t, we should not get confused. So let's leave it like this. A dot This is 0. And when I write the equation for the x, similarly there will be equation for the y. They will all be same. I have a 2 because I get gamma tx and gamma xt. So you get a 2 over a and dt over d tau, because the Christoffel is gamma tx. So once you get a dt over d tau and once you get a dx over d tau. So these two are the geodesics. You can also add y and z. They are exactly same as this. Now, let me give you one particular solution. So if I write this, a solution, a very simple one, t is equal to, let's say, alpha tau. So I'm making a straight line, and x is equal to x naught, y is y naught, z is equal to z naught. So in other words, if I suppress y and z, you can take them to be 0. Then it is these lines, straight vertically up. So it's a solution. Straight lines in these coordinates, vertically up. However, any of the slanted lines, slanted straight lines, they are not a solution. Because first of all, let's check that this is a solution. So t dot is alpha and t double dot is 0. X dot, y dot, z dot is 0, and so are the double dots. I should, this dot is not with respect to time, this dot is with respect to, let me write it explicitly. Let me define, instead of writing this full thing, t dash is dt over d tau, and similarly, so then from here, t dash is alpha and t double dash is 0, and x dash is equal to y dash is 0, and the geodesic equations are t double dash plus a dot, t dash square, x dash square plus y dash square plus z dash square is 0, and x double dash plus 2 a dot over a, t dash x dash plus y dash plus z dash is 0. So you can see that since this is 0 and these guys are 0, so the first equation is satisfied. Similarly, this is 0 and this is 0, so second is also satisfied. So this thing is indeed a solution. But if I take a slanted line, and let's say you have some x, we can keep z and z naught still, y and z still constant. So it's a slanted line. Then you have t dash is alpha, t double dash 0, x dash is beta, and x double dash is 0. So the first equation over here is still satisfied. This is equation 1, this is equation 2. Equation 1 is still satisfied. Is it? No, it's actually not. Equation 1 is not satisfied because t double dash is 0. Then you have a dot and x dash is beta. Beta square is 0. Now, unless I assume that a dot is 0, a cannot be 0 because if a is 0, then this metric is a singular metric. This was the metric. So if I put a is equal to 0, this is like crushed, a singular matrix. So that I don't want. A is not 0. And if a dot is not 0, which I'm assuming this a has some time dependence. It's not independent of time. Then this can only be satisfied if beta is 0. Possible if beta is 0. But that would be a vertical line. That wouldn't be a slanted line. That would just be a constant x equal to 0. So this is not the case. So this is not a solution. A slanted line is not a solution. And you can check the other equation is also not satisfied. So slanted lines are only solution if a is a constant. It doesn't have a time dependence. Now, we haven't obviously found all the geodesics because we know that starting from any point, I can point in any direction and there will be a geodesic coming out of it. All I have proved that these vertical geodesics I know, which start vertically, this remain vertical. The geodesics in other directions, they are not straight lines in these coordinates. They are not, when I say they are not straight line, I mean they don't look straight in this tx plane. They have some kind of a other form, which I haven't explored. I don't want to go into that. I don't want to find all solutions. All I have shown is that those lines are not geodesics. Now, let us see how does the light behave. Light's behavior or light's motion, light's dynamics in this space-time. So now, how does the light behave? Again, I use what's the law for the light? Again, go to the initial coordinates. So in the initial coordinates, I know that the light has this property. That is just saying that the speed of light is 1. In inertial coordinates, metric is just the usual metric. So all the special relativity is valid. All you do is write the special relativity laws and write it in tensorial forms. So the law of special relativity, which said that the speed of light is 1, is this one. But this, I know, this is ds square. Because I'm in inertial coordinates, so I know that g is this. So I can pick up these coordinates and write the same thing like this. When I will open them up, I'll exactly get this. But once I have written it this form, this is a tensorial form. So I get the law. The law is ds square should be 0, or this guy should be 0. And also the path should be a straight line. That's always given, because in special relativity, the law is that the light's world line is still a straight line. It's just that it's a very special straight line. It's at the 45-degree. When I go to a general, but that this statement about 45-degree is not coordinate independent. It's not even true in flat space if I go to funny coordinates. We saw that when we change the coordinates to accelerated coordinates. So the coordinate independent statement that the light follows straight line at 45-degree becomes this one. So it says light follows geodesics, which are the straight lines without any reference to coordinates, which are null. Null is just a word for this fact. That if I parameterize my light's world lines by lambda, then this is 0. So very secondly, people say light follows null geodesics. So this is again the use of equivalence principle. Go to the initial coordinates, write the special relativity law, and just change that law into a coordinate independent shape, and then you will get the law. Now, in the coordinates that we are given, in the metric, in the space-time we are given, in the space-time and the coordinates, we are given. By the way, this is true for all spacetimes because I didn't derive it for our metric. It's true for any metric, any spacetime. But in the spacetime and the coordinates we are given, this statement that ds square is 0 translate into, when I open this up, so suppose I am looking at the motion in the x direction. Let's suppose that y and z values are fixed. Whichever way the light is moving, I'm calling it x. So this gives me minus dt square, because the metric is diagonal, you have a g00 term, gtt term, which is -1. Then you have a gxx term, which is a square. So this is the nullity condition. So I have to look for geodesics which also satisfy this. So find geodesics which also satisfy, which are also null. Null, that is, satisfy this equation 3.
एक्सक्यूज मी सर
जी,
सर 5 मिनट का ब्रेक मिल सकता है
क्यों?
मुझे काम है बस मैं 5 मिनट में आ रही हूँ मुझे समझ में नहीं आएगा अगर मैंने बीच से छोड़ा तो 5 मिनट
I don't know, what do other people think?
ठीक सर, हम भी नमाज पढ़ लेते हैं 5 मिनट।
ठीक है,
जी सर
फिर
5 मिनट्स का ब्रेक दे देते हैं
ठीक है, तकरीबन 10 मिनट्स का ब्रेक ले लें।
थैंक यू
ओके सर,
Thank you.
थैंक यू।
So we have to find the geodesics subject to this condition 3. We have this extra condition. So this condition gives me dt is equal to plus or minus a dx, right? Now I can also write, I can divide by the parameter, and this is just this statement about the tangent vectors. So if I want, I have this condition, and I have to solve the previous geodesics subject to this condition. Now let me give you a solution. So the solution is, take t dash, which is dt over d lambda, equal to a constant, which I'm calling omega naught over a. Then by nullity, I know that x dash, which is dx over d lambda, has to be omega naught over a square from here, plus or minus. So I'm just choosing the plus branch. One can just put the minus in. Now I want to check, is geodesic satisfied? Nullity is satisfied because that's how I derived x dash. So this is 3 is satisfied, and I have to make sure that the geodesic is also satisfied. So t double dash is minus omega naught over a square dA over d lambda. So this is minus omega naught. I can bring in through chain rule a derivative with respect to t, because from here this also gives me, I can write it as t is equal to omega naught over a lambda plus c if you want. Similarly, you can solve that. So lambda becomes, because lambda is the parameter on a line, so I'm remaining on the line, I can pick up the t. So lambda becomes a function of t and t becomes a function of lambda from here. So I can bring in through chain rule a d by dt over here. And this gives me then minus omega naught over a square, and it's a derivative with respect to time. So this is a dot and this is t dash. So T dash is T dash from here is just omega naught over A. So I have got omega naught A dot over A cube. And first equation, equation 1, what was it? It was T dash plus AA dot X dash square. Is 0. So T double dash is minus omega naught A dot over A cube plus AA dot X dash is omega naught over A square. So X dash square is omega naught square over A4. So this is 0. Satisfied. Now for second equation, for equation 2, I have X dash, I start from here, I have to construct X double dash. That is, I have to construct this guy. Second derivative with respect to the parameter. And remember, since it's the light, so I'm not calling the parameter. You don't have to call it proper time, but I'm just even denoting it by lambda. So X dash is given as 1 over A T dash. X double dash is minus 1 over A square dA over d lambda T dash T double dash. And again, to bring in a dot, I can use the chain rule. So this becomes minus 1 over A square, A dot, and this becomes also a T dot, T dash, so T dash square, plus 1 over A T double dash. Therefore, second equation was X double dash plus 2A dot over A T dash X dash is 0. Let me just confirm. Yeah, plus T dash X dash. So instead of X double dash, I put in here and I get minus A dot over A square T dash square plus 1 over A T double dash plus 2A dot over A T dash, and X dash is T dash over A. So I can write it as T dash square A square. So this adds to this, and I can multiply with an A. So this gives me T double dash plus A dot over A T dash square is 0. But T dash over A let me look at the first equation. It's over here. You have x dash square, and t dash is a x dash. So this is equal to this is just 1. So equation 2 is equivalent to equation 1 once you impose the nullity, and equation 1 is satisfied. So that means both equations are satisfied. So the solution I had written was a proper null geodesic. So this thing, let me write it again. And x dash is a null geodesic. Now I have given it just the tangent vector of the null geodesic at every point, but you can integrate it and plug in the lambda. So would be this would be the curve. Or maybe just leave it like that. I've just found the tangent vector of it, not the curve. Now, this guy, this tangent vector, for the case of light, we were calling it, we were giving it the symbol p mu, this vector. It has two components. The other components are 0, or you can say I'm suppressing them. And these are omega naught over a, omega naught over a square. And this is tangent vector to light world line. And since in case of light, we decided not to have any West mass hanging over there. So the tangent vector directly, we called it the 4 momentum. It's another name for the tangent vector in case of light, which is fine. And we decided that we will choose lambda so that this is now in case of flat space, in case of special relativity. We decided we will choose lambda so that this thing let's call it omega and dx, this was same in case of flat space because this is the null vector. This vector is null. Using the metric, this is 0. And we said that the light's vector has to be null, so it has to take this kind of form. And we said we will choose lambda so that the derivative, the number which I get for each component, the both components have to be equal, but the number which I get for the component will be equal to frequency of the light. This is how we are just by convention going to scale it so that the first component gives us the frequency of the light. Now, this is the frequency according to an observer who is assigning the components dx over dt and dt over d lambda and dx over d lambda, or drawing the path t lambda x lambda. So there's some x, some t. I'm in special relativity, and he's drawing this path, these components t and x. For him, this frequency is omega. Now this observer, his own world line is this one. Then his forward velocity would be in these coordinates, because these are his own coordinates, is 1 0 0 0, right? This is just dx dt over d tau dx over d tau scaled with and properly normalized, which you do by scaling with that's his forward velocity, which we know has to be normalized, which it is, because the metric is flat and you have so on, so equal to -1. Now I can write this frequency. Now this is the fun of using the equivalence principle. Equivalence principle, and the other thing which I was saying, write everything in terms of tensor. That sometime Einstein used to call it another principle, but it's so obvious now that people don't even call it a principle. It's called the general coordinate invariance, that your equations should take a form so that they are true in all coordinates. So this fact that this is the frequency they are measuring, I'm going to give it a form of some kind of a general coordinate invariance statement. So I can write the frequency measured the frequency measured by this observer as so it's just omega, but I'm writing it in a funny way. I've put in 2 minuses and +1, doesn't do anything. But this minus I keep right that, and for this guy, this is d0, 0, because d0, 0 is -1, and this is u0, this is u0 because u0 is 1. But you can also add in g11, u1, u1, w. Now, because how could I add this? Because u1 is 0. So this I can write as u0. Well, I don't want to write it as u0, u0. Let's write it. Let's use 1, 1 over here. This omega is p0, because remember this p0, p1, this thing for this guy is omega, omega. So this is just this thing. Now that I have written it in this way, this has become, you can also call it minus p mu u mu, same thing as this. But this is now true in any initial frame, because it's a tensor kind of equation. And what is this equation saying? How did we derive this equation? This equation was the frequency measured by an observer whose forward velocity was given by these components. Then the frequency they measure is given by this. But now this is true in any natural frame. So for an observer whose forward velocity is given by u mu, whatever the components are. So this is not the component, this is not an observer who is in the original coordinates is at rest. Frequency would still be given by u mu pu nu. For an observer whose forward velocity is given by u mu, when a photon passes by, whose p mu in our frame is p mu, then that observer will measure the frequency to be this thing. But then this equation is valid in any coordinate system, and in any, it's a tensorial equation. So the principle of equivalence says that true in any space-time. Now, what we had in our case, if I consider those guys to be observers, I found some geodesics. So I suppose that these guys are I have placed some observers here. So these are the world lines of some observers. And these guys, they don't feel anything. They are, what you can say, they are in the free fall because they are following the Newton's law. They are following geodesics. They're following straight lines. So they're not feeling any forces. So they just are floating around in this space-time. And light is passing by. So what kind of, by the way, what kind of shape the light takes? The light has, if I start from any place, the light cones are of this form. They're going flatter, they're going vertical with time. And in the past, they become more and more like this. If A is a monotonically increasing function, this is how they will look, right? They're not normal kind of light cones because of this relation I had. T dash was X dash times A. So, so suppose we had put an observer at over here whose world lines we had found. So for those guys, dx mu over d tau was 1, 0, 0, 0. Well, actually, I had put an alpha over here, over there. So you can say alpha 0, 0, 0. But then u mu has to be normalized. So if I use this, I have to construct, I have to make sure, because that's the definition of the forward velocity. Forward velocity is the tangent vector, which is normalized to 1. So I get g0, 0, which is -1. And then I have some u mu, I'm taking it to be some constant times dx mu over d tau. So it's, I don't even have to do it. You can see it. If I choose c to be 1 over alpha, so that this alpha cancels, I will have properly normalized. So that means actually it would be better if I had taken this solution for the curve. These are constants. That would have been slightly nicer in the sense that when I will compute the tangent vector, it will already be the unit tangent. So suppose I have done that. So u mu in any case turns out to be this, even if you start from here, because you have to divide by 1 over alpha to normalize it. That's the unit tangent. So the frequency measured, and I have also figured out that the p mu light's tangent is this. Then what happens is the frequency measured for the light would be minus g mu nu dx mu. This was the formula. U mu p nu. So I get minus 1 minus 1. U is just as this one component, and p0 is omega naught over a. So it depends on this parameter t, parameter a. So that means if there's this observer, there are these two observers, and light path is crossing them. Over here, since I have these solutions, t is equal to tau, and x, this solution is t is equal to tau, x is equal to x naught, and this is t is equal to tau, x is equal to some other x value of x, x1, which is a constant. So you have dt is d tau and dx is 0. But I know that the proper time, how to measure the proper time? Proper time is minus g mu nu dx mu dx nu. So I'll have minus 1, and only dt square. So that means d tau is just dt, or tau is equal to t. That the proper time measured by these observers will be same as this universal parameter t. So this I can very well call them. They all agree on this clock's values at these interval, these events, wherever they cause them. And A has a certain value here and a different value here, AT1 and AT3, where it causes. So what happens? This light, when passes through the first observer, he assigns it a frequency omega naught over A of T1. And when it crosses this second observer, he assigns it a frequency omega naught A of, let's say, T2. Let's call it 2. So omega 2 over omega 1 is omega naught over AT2 times A of T1 over omega naught. So omega 2 over omega 1 is A of T1 over A of T2. So if A of T2 is bigger than A of T1, then omega 2 is less than omega 1. So this is called the redshift. So actually, what I have written over here, this metric, this is what was observed by Hubble, actually. This is, let me first write that. This is actually the Hubble's redshift. And this metric, which I had written in the start, is apparently the metric describing our universe. And our galaxies are these kind of observers, which are freely floating. And they are these kinds of geodesics, which are not changing their coordinate in this coordinate system, in which I have written the metric. So what happens is a galaxy at this point, at this time, sends out a light signal. So it's a, for example, a hydrogen light. We know what it is, what its frequency is supposed to be, a particular hydrogen line. But when this light crosses another galaxy, so for example, it starts from a faraway galaxy, and when it reaches us in our galaxy, by that time, A has changed. This A is called scale factor. A has increased, so what we see is that the frequency has decreased. We do not see the same frequency as we were expecting from a particular, from the hydrogen. We get it to be less than that. And the more we wait, the more the change, because it depends on this ratio. So if I look at a nearby galaxy, then this intermediate time, the A is not that small compared to the A now. So the change in frequency is small. But if I look at a faraway galaxy, the change is bigger. And you can derive the Hubble's law, which I have put in the homework. But the main idea is that the light's frequency redshifts. So the way they describe in popular science, that's not the correct way to think about it, that the light is being redshifted because the galaxies are moving away. Probably the best thing, the right thing picture, well, I don't know what is the right picture. This is just our prescription. The prescription tells you how to deal with the geometry, given the metric. You just draw the thing, the coordinates over here. These are the log lines which you get for the galaxies. And it's just that the geodesic equation is telling you that the light's frequency should keep getting redshift as it crosses you. Now, maybe we should stop here. Let's stop here. Is there any question?
No, sir.
Okay, let's stop here.